how many meter per second, or the acceleration due to gravity. So these are entirely multiple different units. So when you merge all of these modalities, the final output value you are looking at is not one modality. So we take bits and pieces. It also depends on the complex context, what kind of questions we want to answer. Then we merge. We call this the data fusion or sensor fusion technique. We use that technique and then pick which specific solution we want to arrive, what is the threshold, how much of latency, and so on. Then we use that. So there is really no standardization available in some way. It's a very hot topic area, actually, very, very hot topic. Daniel SCN, who is starting in January, he will be looking at multimodality as part of his PhD thesis. All right. Any other questions for Venkat? Rajesh, is that your old hand still up?
I'm sorry, sir. It's a whole man. Thank you. Thank you very much.
Okay. All right. Hariesh, go ahead.
Yeah, I'm just presenting in a minute. Your screen visible?
Yeah, now it is visible. Yeah.
Yeah. So good afternoon, everyone. Today I'm going to present on a topic that's not only innovative, but also has a potential to transform one of the most critical agriculture industry, which is dairy farming. And my presentation is titled Leveraging Large Language Models for Behavior Analysis of Cows. I am Hariesh Sivakumar. I am a graduate student in the second year in Dalhousie University, and I'm excited to share how advanced technology is helping us address the long-standing challenges in the dairy industry. So basically, as of 2023, dairy farming is a 8.56 billion US dollars industry, where productivity heavily depends on the health and the well-being of its most important contributor, which is the cow itself. And the health of the cow and the behavior of the cow are pivotal to maintaining the productivity of the farm, and they are very correlated. So monitoring the cow behavior becomes very crucial in this aspect. And it monitoring allows the farmers to detect any health anomalies and take corrective actions to improve the farm's efficiency and also the animal welfare. The traditional methods which are being used as of now are the manual methods are inconsistent and are prone to inaccuracies. These inaccuracies delays the decision making and can lead to high cost if issues are not caught in time. So this is where our solution comes in with technologies like vision transformers and large language models. These tools automate monitoring, and they uncover patterns and nuanced behavioral changes, and provide actionable insights, enabling the farmer to make proactive decisions with ease and with not a lot of knowledge regarding the technical aspect of it. And unlike the current methods in the market, which analyze the single behaviors in isolation, our proposed framework offers a holistic view of the whole behavior. And current approaches rely on sensor based monitoring systems or traditional machine learning models that focus on analyzing single behavior in isolation. While these are useful and have great accuracies, but these fail to uncover the patterns over time and the behavioral changes over the temporal in the temporal aspect. So this gap is where our proposed framework shines. It integrates the spatial capabilities of vision transformers with interpretative and temporal analysis power of large language models to revolutionize behavior monitoring in cows. The goal is to automate, simplify, and enhance the decision-making process for farmers, enabling them to respond promptly and effectively. Together, these technologies analyze behaviors such as standing, lying down, and transitions between them, and detect if there is any anomalies based on the total herd health, and predict risk and recommend solutions, effectively automating and enhancing behavior monitoring. For example, this framework can identify subtle changes in behavior, like cows spending a lot of time in resting or showing signs of stress, or provide early warnings and recommendations to address this. To validate this framework, we used cow behavioral video dataset 5, which is available on Kaggle. This dataset includes 8,696 images of cows with 5 distinct cow behaviors, and the cows. I guess there are around 700 cows in this dataset. And to improve the model's performance and generalizability, we augmented the data to create 50,000 training images and 15,000 test images. The images are passed through the vision transformer model, which is already pre-trained on ImageNet, which has 21,000. It's trained on 21,000 images. So this transfers its knowledge to identify the nuanced behaviors such as posture changes that may indicate stress or discomfort. The images are then converted into resolution of 224 into 224, which is the resolution which vision transformer model expects as an input. And these images are split into patches, which I'll be explaining in the later part. So basically, to understand patches, the images, we can, in a layman, we can say like there is a grid type of structure in the images, and each the image is separated into those grids, and each image which is split into patches are sent separately, and they are changed into lower dimensional linear embeddings, and this embedding goes into the transformer encoder, which has a self attention mechanism, so which tells the transformer encoder what are the areas which it needs to pay more attention on. For example, if we look into the picture, so if we look in, for the basketball, it tells the algorithm to focus on the ball area where where the information is there, which is helpful for the classification rather than the background noise. So this happens in the encoder, and from there the classification is passed on to the high level perceptron, and comes out of the classified output. And the output from this model, which includes cow ID, behavior, and the timestamps. So this output is passed on to the LLM, where I have used GPT-4 legacy model to identify patterns, anomalies, and any actionable insights from that. So, for example, if there is any increased restlessness or extended inactivity or in any infrequencies in particular action, that might be flagged as an anomaly by the LLM, and it will notify the user. So, if we look into the models more deeply, so basically, VIT is a cutting-edge deep learning model by Google, which was originally popularized in natural language processing. So that's why it is converting the images into patches. Just like how in NLP the sentences are processed as like small words are taken, and those words are looked for any if they have any for the mean captured for local features. Then as a whole, it's also checked for the a global feature. That's exactly how it happens here. So first, each patch is checked for any information from there, and as a holistic view, it is also seen for the whole image. And by leveraging like the transfer learning from the large data sets like image net, which it has been already trained on, and while we fine tune it on our model, it on our data set, it can easily detect the subtle nuances in the images and making it ideal for this cow behavior analysis. And it identifies patterns with regard to the temporal feature that may not be obvious through traditional machine learning models, such as changes in posture or movement that indicate stress. So, and this is also proven to be computationally efficient and accurate than conventional models, providing critical insights. So why I chose GPT-4 for large language models is it has proven to analyze patterns and relationships between behaviors such as like connections between restlessness and any environmental stressor which might be there. So these patterns which are can be captured really good by this model, and this interprets like the data output from VIT to actionable insights, like identifying what are the anomalies, why it was caused, and what are the steps which can be taken. And it also it can be acting like a decision support system where the user can actively ask what needs to be done and communicate with that based on the uh, analysis it has already done. And this can provide domain-specific insights by learning patterns from diverse datasets. For example, in this dataset we are using behavioral dataset where we have 5 different behaviors. So we can also expand it to any other dataset and try to combine them, because it'll try to find patterns between the other diverse datasets and come up with a better analysis. And it provides like recommendations like health checks and environmental improvements. It also lets know if the anomaly is a priority or it can be made sure. So it can analyze if it's like it analyzes the herd health and checks if it's like a very big of anomaly, and is what actions need to be taken, or if it's not a very prioritized, which helps in informed decision making. And the beauty of this is the ability to generate insights in natural language, making it easy for the farmers to understand and act on. And so basically what happens is so we are integrating this into a as a multimodal framework compared to machine learning, where you have to just insert the visual data and not able to interact with that. And this automates the behavior analysis and reducing the reliance on manual monitoring and sensor based systems, which can be expensive and not scalable if the herd size is changing in different farms. And this has proved to large language models have proven to identify deviations in behavior patterns and analyze the behavioral changes, and as explained, like the providing recommendations for that. So the key findings which are found from this data set was first the LLM was so the basic flow was after the LLM is fed with all the details like cow ID, behavior, and what are the timestamp and how much duration it was in that behavior, and what was the transition after that. The LLM learned all the things and gave a first it was asked to give an holistic finding for the whole farm. This can be useful to verify how well it has understood, and also it can act as an ideal situation or an situation which can be labeled as normal, and to check how deviating the other cows are. So what the general things were found as the most alternative transitions was between standing and lying down, where standing was most, which is evident. We can see from the most of the farms we have visited, and there was a predictable pattern between activity and rest cycle. For example, if a cow is standing, the next would be either lying down or ruminating, and for foraging it will be lying down and ruminating. So there is an active, and most of the cows would go from like activity to would not go from standing to foraging. It will lie down and they'll go. So that was a pattern which was analyzed, and the peak activities in the transitions was so basically in this data set, the time frame was split into 7 different intervals. So we were able to see that in the 3 to 7 was where the most activities were done. So the 1, 2, and 3 was not a lot of activities. So basically, if a cow is standing, it prefers to stand for the 3 intervals in that time. So that it may indicate any environmental things happening in that farm, or maybe in the early of the day they are not very active. And most cows have been observed that to stay in one behavior irrespective of the time for on an average of 3 intervals. And so this also can let us know that if there is any cow which stays for just 1 interval or stays for 6 intervals, it is an anomaly. Either it's feeling anxious or it is lame. So these can be found. And next, the model was asked to identify the anomalous cows and why it is flagging it as an anomaly, and what it thinks that might be. So different types of problems were given to like ask, like, what are the anomaly, why do you think so, and what are the possible causes that it might be thinking of. And it was also asked, what suggestions would you give to the farmer, to what would be the next steps. And the outputs like I have listed out 3 anomalous cows and what was the thing. So basically for cow 1, it analyzed that it spent minimal time in lying down and ruminating. So most of the time it was standing still, and there was not a lot of rest in that. So it might be an indicator for like a digestion issue or a rest issue. So the causes can be stress, discomfort, or any health issues which it might want to be checked. And so this is not a very abnormal thing, because we also have a constraint that this data set is not like a very vast data set where we can understand. Maybe in that time frame it didn't ruminate or lie down, but this is flagged so that it can be verified to check if there is any bedding comfort, or if there is any metabolic disorders, or any changes, any frequency monitoring changes which has to be changed, so that it comes under all the behaviors come under the time frame. Next one was like the cow 89 there was a rapid change transitions for it. It was lying down and standing in every interval, so which makes it like that it is either very anxious, or there is any stress, or it is frightened, or any discomfort, or something like that. And this was flagged as like an important like a high priority, and it was like we have to inspect the cow for any possible stresses. If it's like if there is any external factor stressing it, and if there is any pain, if there is any like a wound or something, and these if it's a stress, this can also lead into lesser yield of milk as well. And for the third one, we saw that cow number 340 was lying down for the most of the time so out of the 7 time periods, 6 time periods, it was laying down, which was the most and very uncommon in the herd, which might be due to an injury, fatigue, or lameness. So this was also flagged as an highly important anomaly, and because this has to be the vet has to check to make sure that everything is good, and it's not any external factors like temperature or any wedding quality or any stress involved there. So this is what findings came from that, and the future direction would be to scale into like as I said, this was done with just one data set. We can the future direction, we can integrate multiple data sets and try to find patterns between different factors, and if that has to do anything with the stress or the yield of the cow. And uh, this the we are also aiming to come up with a real-time dashboard, like so for example, if it like it keeps on updating on like like a loop, keeps on updating the analysis, because now we are feeding on whatever data set we have. So that would be a more insightful like a application for this. And to and the third would be to like to make it more modality features for like sensors and voice data, like the sound data, to understand if there is a relationship between that. And the sensors would be very much useful, because if we can know what's the temperature and like what axis it is standing and so those would also come under the, if it's stressed or if there's any fever or something like that, so that can be used. In conclusion, our framework integrates like visual transformers and GPT-4 to revolutionize behavior monitoring in dairy farming. By automating analysis and providing actionable insights, it can help the farmers to make informed decisions that enhance the productivity and promote animal welfare. Thank you. I'm happy to take any questions.
Any questions for Hariesh?
I have a question.
Go ahead, Shubhangi.
Yeah.
Shubhangi, we cannot hear you. Are you asking questions?
What does your data set look like?
Sorry?
Yeah, I was asking that how does your data set look like? Like how do you train your LLM?
Okay, so basically, dataset compiles of 826 videos. So those videos are like too large to process. So what what the dataset also had was another folder in which they had splitted that into an equal intervals of 7 time intervals for the same specific data. So for let's say we are taking cow number 1. So we have a video of cow number 1, but also we have 7 in like equal intervals of that cow. So that is now then we have 7 images of the same cow that is used to first to fed into the vision transform model to understand what's the behavior of that. Is it standing or lying down? So now after that we know what is the behavior of that cow in that time period, and what's the time period between that. We get all the information regarding that, and that's fed into the LLM for analysis.
Any other question, Shubhangi? Does that answer your question? It seems there is a net connection. It seems to you a bit frozen, Shubhangi, at your end. Are you able to hear us? Well, let's move forward. Sibi, go ahead.
Yes, I had a doubt in the mid of the presentation. By intervals, 3 intervals, 7 intervals, you meant the number of frames each video was divided to, right?
Yeah.
And were the cows given specific IDs?
Yeah, every cow has its own specific ID.
Oh, okay. That's what I was wondering about.
Okay.
Thank you.
I have a question. What is the computational power that is needed for this? Like, are you using a GPU or?
Yeah, I am using like a Collab Pro with GPU, like high
Okay.
RAM to run that. Yeah.
And how long does it take to run usually?
For 20 epochs, it took me around 4.5 hours.
Yeah.
Like approximately.
Okay. Thank you.
Yeah.
Any other questions for Hariesh? So GPT recently released a new subscription 01 model, which is $200 a month subscription. So you say you can actually do voice plus text plus image, all three, kind of going towards multimodality, more advanced reasoning capability, and so on. So it's kind of along these lines. But some of the results, in terms of visually comparing, I know, for example, in this particular slide, you have some charts, plots, graphs, etc. I don't know whether these are from your images or just a
Just
symbol to show
mock-up,
what's can be done. So similarly, if you could show more visual way of comparative analysis of your results, so that would be more appealing to the audience, more scientific to convince the reviewers.
Okay.
All right. Any other questions for Hariesh?
So I'm basically looking into in the previous for Venkat, Shreya asked like how would you like come up with evaluation for that. So I'm looking into like I'm trying to see if the LLM can predict what's the next behavior of the cow, and giving I'm making it as a test for giving just 6 of the intervals and trying if 7th one is going. So I'm evaluating if that on that basis if the understanding is good. So I'm coming up with that. But in future that may give up more like tables and visual things.
Okay, all right. Next is it Shubhangi?
Yes, Professor.
Is your internet connection good? It seems to be a bit disconnecting for us.
Yes, I think so. Like I'm connected with. I don't know what's happening. It should be good.
Yeah, go ahead.
Yeah. Is my slide visible?
Yes, we can see it. Yeah.
Yeah. Okay. So hello everyone. Today I'm going to talk about DairyDigiD, a biometric classification system for dairy cattle using DenseNet 121 and Detectron 2. Here, Hangjin has made a big contribution, and it was done under the supervision of Dr. Suresh Neethirajan. Our research objective is to develop a deep learning system which can classify the cattle. Right now, we are currently classifying them into 4 categories: young cow, dry cows, mature milking cow, and pregnant cow. This is done based on the facial features, but this, the introduction, first we'll have a look at the introduction of biometric classification. So biometric classification is a technology that uses the unique features of individual thing and then use it for identification and categorization. In the context of cattle, here we talk about eyes, nostrils, like which we know as a muzzle area, ears, and more. Then the current challenge that we face in our dairy industry and dairy farms right now is like traditional methods, usually like ear taggings and branding, have long-term used by farmers and ranchers. However, these methods present several limitations. So the ear tagging and branding can cause a lot of pain and discomfort to the animals and potentially leading to infection and stress. These can be error prone as these tags can get lost, damaged, and the incorrect data will eventually lead to the wrong analysis. It's labor intensive, manual data entry and record keeping can be time consuming, and it's prone to human error. The limited data, traditional methods provide limited information about an animal health, behavior, and genetic makeup. So the data collection, the data was gathered from the local dairy farms in Nova Scotia, and these were around small to medium farms, which has 60 to 110 cows per farm. The data set mostly consists of the Holstein cow with some of Jersey cows present there. And it has different age groups. As I mentioned earlier, it categorized into 4 categories: young cows, mature, pregnant, and old cows. These are the number of images we had. For young cows, there were 266 images, mature 1,315, pregnant there was 89, and for old cows, there were 625 images. So what are we doing? First, we are implying the DenseNet 121, which is a good classification and gives a good accuracy, but it has little limitations, which we'll talk about later. Then coming on to the Detectron, which mainly focus on the facial features and is expected to be more robust solution for cattle identification. So before knowing our results, let's have a look what is a DENSE 121 is. It is a convolutional neural network. It gives a good opportunity where there's a problem of a vanishing gradient. So in this, the dense block, each layer is connected to the next layer so that every last layer has a little bit of it on the next one and there's no vanishing gradient. Then there's transition layer. In transition layer, we can see there's mainly 2 purposes: reducing the number of feature maps, and second is downsampling the spatial dimension of the facial features. These help to properly perform the data, properly perform the analysis. So the result of a DenseNet 121 was very exceptionally good in categorizing the 4 categories. So it achieved accuracy of 98.1% in training and 97 in test accuracy. The challenges that we faced were some of the cattle were misclassified and there was overlap between young cows and pregnant cow. And our assumption is maybe this could be because of the background features, because most of the farms have almost the same background. The images were taken from few farms. Then further, we use some explainability tool. Here we have used GradCam. So as you can see, the highlighted area shows how the model is learning. Here we have given the full image. We're not specifically focusing on the facial part. So in the first image, you can see the model is learning from the leg, but in other images, mostly it's from the face. So then we thought that the facial features plays a major role, and we started to focus on the facial features. For that, we used key points and annotation. We have selected 30 landmarks were chosen to represent critical biometric features such as the eye, nose, muzzle area, the head, the alignment of the face. For this, we used CVAT tool, and which was precise and manual annotation, which marked manually for areas like ears, eyes, and has a bounding box in the end. So this is the Detectron 2 architecture. First, we input the image. Then there's a backbone and different layer of ResNet is performed in it. Then the FPN is a feature pyramid network which abstract features, and that takes a single scale image per time. And then it goes through the regional proposal network which focus on the specific areas. And ROI is the region of interest. It finds out where the model should be learning and next perform the next steps. Then the results of the Detectron 2 were also very good. It has high performance for mature milking cow. Maybe this is because the data set of the mature milking cow was more comparative to other categories. Young cows were slightly low precision and recalled due to the overlap, which we talked about earlier in the pregnant cow. And pregnant cows' performance attached by the dataset imbalance and subtle feature differences. These are the comparison of confusion metrics. So we can see DenseNet perform comparatively better than the Detectron 2, but as mentioned earlier, the environmental factors play a major role. And when we specifically focused on the facial areas, where we use Detectron 2, The confusion matrix still performs better, and the accuracy was around 93%, but it's less than DenseNet. Then for DenseNet, the process is done on the entire image, leveraging both facial and environmental factors. The performance will overlap, but may rarely rely on non-facial clues. And the Detectron 2 focuses on fine gradient facial remarks, annotated key points, which we told the model like specifically to focus on these specific areas, and robust against environmental variability, but struggles with visually similar categories like pregnant cow and young cow. So what did we learn from all this? So the DenseNet Insight as a baseline model help us like get a proper foundation from where we can start and further look what to do next, improve the performance by leveraging the border images features and capturing the environmental clues that aid the identifying cattle behavior. Detectron 2 effectiveness. The study demonstrate that particularly mature cow did very well when we used the facial features. With sufficient data, the Detectron 2 can give a promising results. Then, sorry for this mistake in video. Then the challenges, misclassification issues arose in categories like pregnant and 2 years old cow, largely due to the visual similarities between the groups and class imbalance. So how can we overcome these challenges? The dataset expansion. Currently, we are planning to expand our dataset. Earlier, it was 250 cows. Now we are planning for 1,000 cows. Expanding the dataset to improve all over performance, especially working on the pregnant category. Exploring vision transformations. This could actually give a better local and global features, improving all over accuracy. Border features integrations, it will give additional features as posture and behavior attributes to enhance model generalization and model explainability. Like we can use LIME or DRISE to increase the transparency and correct biases. So what is the novelty of our research? The innovation use of DenseNet 121. So this captures both facial and environmental features and has a great classification performance. Second is facial landmark based identification. Here we use 30 facial landmarks for mature milking cows. It's performed the best in it and has fine gradient accuracy. The third is we are integrating the advanced object detection framework, which is Detectron 2, which helps in cattle classifications, cattle classification, specifically focusing on the facial areas. So as there are also some limitations, so our data is little imbalanced and we have some misclassification, specifically on the area of pregnant cows and younger cows. So we'll have to work on that, and the environmental factors play a role in DenseNet, and due to that the model sometimes learn from the environmental rather than focusing on the main clue. Visual similarities between the categories. So the cows have visual similarities, so we need to give more data sets so it can learn better. Data quality, which will be insufficient represent for a particularly less represented class like pregnant, and data expansion will be needed for that. Scalability in diverse farm environment. The model's effectiveness may vary in different farms environment due to influence of external factors such as lighting conditions, the camera angles could be different, the background variations, and the scalability. Computational resources and processing time, because both the models are advanced models and requires significant computation resources, which may limit its applicability for real-time monitoring in the farm system. What next? We are planning to expand our data set and work on the data set of 1,000 cows. Next, we'll have explainability tool, which can give explanation on how the model is actually performing and how it's learning. Accordingly, we can set parameters and learn from there. Third is future integrating additional features, body postures, activity levels, and emotional state. And then is vision transforms with their ability to encode local and global information. Thank you, and I'm open to questions.
Okay, thanks, Shubhangi. Questions for Shubhangi? Go ahead, Sibi.
Hi Shubhangi, it was an interesting project. I had a doubt whether you're working only with static images or continuous monitoring video footage too. And is this project mainly focused on monitoring or identification?
This is a nice question. So currently I'm working with the static images. We had some video images and we had some videos. So we use that to extract data frames from it, images frames from it, and use that for our data set. Then it's a classification project. So mainly we are trying to classify the cattle into the categories, and it's object detection as well. Like from the environment, you're identifying that this is the cow, this is the cattle. We are wanted to, then we will classify that further.
All right. And what's the reason to choose face as the identifying factor for the cow?
Okay, so in starting, when we use DenseNet 121, then when we applied the explainability tool on that, most of the model learning was based on the face. Some were learning from maybe the neck, the leg area, but most, like around maybe I'll say 80 or 90% was learning from the face. So we thought maybe if we go more into the face, so the model will learn better. It's like a facial recognition for cattle.
All right, makes sense. Thank you.
Okay, any other questions? Face for human beings, they say face is the index of mind. So when we look at human being identification, when we cross the airport, they take picture of the face, some fingerprint, there is a biometric ID, even hair. If there is a murder or some incident happens, they take just a droplet of bodily fluid, semen, blood, urine, sweat, and then do a DNA testing to identify whether it's a male or female. They can even say whether it's a deceased human being or a healthy human being. All kind of analysis can be done. From a large scale production perspective, it is necessary to classify the cattle. Right now they put ear tags and collars to identify, but if there are 800 cows, 1,000 cows, we want to know who is that. Is it Lotus versus Rosie versus Jessica? Can we be able to classify, identify? Number one. Number two is emotions. Face expresses the internal makeup of the mind of the feeling component of the cows. So whether it's frustrated, happy, sad. If you look at the other body postures, walking, the gait analysis, yes, it does say whether it's pain, very gross level. But if you really want to know the positive behavior, we always focus on the negativity, pain, and suffering. But if you want to know whether the cow is playful, joyful, more subtleties, more nuanced understanding of emotions, affective states, face provides that information. The blink of the eye white regioning, surprised, the posture of the ear, so the tightening of the snout, the upper jaw, lower jaw. So all of these facial indicators, cues, tells us how she is feeling. So that's the reason for choosing face rather than the overall body. But of course, we have to combine both overall body and the face. From the human being perspective, when you talk about class imbalance and looking at more data, especially a pregnant cow is very low. If you look at the human, no, I'm just anecdotal. There is no scientific. Maybe there is scientific evidence. When a female is conceiving, maybe she is 1 month or 2 month pregnant. It's not physically bigger. It's like you don't see that physically from the stomach perspective, but there is a glow. Grandmother or friends can identify, hey, what's going on? You're glowing or you're conceiving. Like that, people ask questions. In the movie also, sometimes say, hey, have you got lucky last night? Something's strange. You feel so good. Those kind of questions they ask. How do they ask? They look at visually. There are non-tangible elements associated to it. Maybe a subtle, gentle smile on the face of the human. They are a bit more dancey, but not very explicitly jumping to the sky. But they exhibit those joy, happiness in a unique way. So Are there cues, traits, indicators, behaviors in a very, very subtle manner buried in the pregnant cows versus a dry cow? Can you be able to look at those based on the neural network, based on the architecture? Can we still be able to unravel? Because these are very, very subtle, very, very small, fine scale changes. But using AI, can you be able to tell it? So you select that maybe you have select the 800 video images of pregnant cows, convert all of those videos into images, and then take dry cow because it's the other contrast. They don't milk; they are at the end of the life cycle from the farming management perspective. Do a compare and contrast. You have step 1 and step 3. In between step 2, which is the milking cow, are you able to see those cues physically based on the annotation, based on the algorithmic analysis? Can you be able to deep dive and write maybe 2 or 3 pages as part of a discussion based on unique analysis? So that would really enrich your thesis discussion when you talk about it.
Yes, Professor.
Yeah. Any other comments for Shubhangi, remarks, suggestions, questions? No? Okay, let's move on to the next presenter. That would be Mayuri.
Let me share the screen. Hello everyone. I'm Mayuri Kate, and I'm in the first year of my master's program under the supervision of Professor Suresh. So my topic is understanding the cow vocalizations using large language models. So cows communicate through subtle vocal cues, which conveys emotion, needs, and intentions. However, deciphering these sounds has proven challenging, limiting our understanding of their behavior and welfare. So there are recent breakthroughs in large language models, which has revolutionized the natural language processing task and enabling them to apply it into the animal industries. So some of the current applications of LLM in animal industries are analyzing the animal behavior data to predict the health issues, developing personalized feeding plan for livestock, and enhancing human animal interactions through more effective communications. Now we propose to adapt this technology to decode the cow vocalizations. So by leveraging the power of LLM, we aim to develop a novel approach to understand the cow vocalizations, ultimately improving the animal care and husbandry practices. So why to use an AI in the cattle industry? So there are some of the reasons why. So first one is then a reduced mortality rate. So AI powered monitoring system can detect early signs of illness or stress, allowing for prompt interventions and reducing the mortality rates. Then the second one is improved reproduction performance. So AI driven systems can optimize breeding programs, reduce calving problems, and increase the conception rates. The third one is increased revenue stream. Precision livestock farming techniques can enable farmers to generate revenue from data driven insights on animal performance, nutrition, and breeding. The fourth one is reduce environmental impact. That is, AI powered monitoring systems can help farmers to optimize the feed rations, reducing the greenhouse gas emissions, and improving the overall environmental sustainability. The next one is an improved nutrition. So AI can analyze the feed quality, quantity, and consumption patterns to optimize the nutrition for each animal, thus reducing the waste and improving the overall health. The last one is on reduced rate. So AI-driven systems can create a customized enrichment programs, providing mental simulations and reducing stress in livestock. So most of the applications is been already implemented by some of our team members. I have read a couple of papers in which I will be presenting 4 of them. So the first one is an animal whisperer, study of Gen AI to analyze the behavior of animals. So this paper explored the use of multimodal large language models such as GPT-4 to interpret the animal behaviors and the body language, focusing on 3 animals, cows, horses, and dogs. So the authors developed the 3 separate GPTs, cow whisperer, horse whisperer, and the dog whisperers. So they developed an app. So these apps were designed to analyze the images of an animals and provide the insights of their behavior and recommendations for human interactions. They crafted a complex prompts with 13 categories, which covers conversation tone, expert knowledge, image analysis, and other aspects. They also uploaded and label image documents and other materials to the GPT knowledge bases for the training for LLM, and they conduct the test in the preview mode by using tag, which is task action and goal approach, to check the app's functionality and accuracy. The second one is the paper presented by our team member Bubakar. It is multimodal information fusion of acoustic and linguistic data for decoding dairy cow vocalizations in animal welfare assessment. So the research paper aimed to interpret the emotional states of dairy cows by analyzing their vocalizations using multimodal information fusion techniques. So they recorded around 1,144 vocalizations from the 20 cows, which are isolated for 4 hours post milking to investigate the frustration in vocalization. Continuous vocalizations were recorded and segmented into individual events by using a Pratt software, which extracted 23 acoustic parameters per vocalizations. And the vocalizations were categorized into high frequency calls, which are labeled as distress or arousals, and low frequency calls, which are labeled as contentment or calm, based on the literature trends. And they employed machine learning algorithms like random forest, support vector machine, and recurrent neural networks to process and fuse this multidimensional data effectively. And they perform the sentiment analysis on the transcriptions, which has been generated by OpenAI's Whisper model, and use the Python's natural language toolkit. The third paper is regarding the vocal behavior in the cattle. So this research paper focuses on the potential of cattle vocalizations to serve as an indicator of their biological process and overall welfare. So cattle vocalizations can potentially convey a range of information, which includes individual characteristics like age, sex, dominant status, and individual identity. Then reproduction status, like information about the reproductive fitness or the estrus condition, potential signals for the need for the resources, and also the emotional states like the expression of pain, fear, and distress, particularly in the situations like branding, isolation, and handling in the slaughter plants. So this paper focuses on the vocalization rate, which could be a useful indicator for the welfare, especially in the settings like in slaughter plants. The last paper is a multimodal dairy cow interaction in an intensive farming context. So this paper employed a multi-species ethnography approach, which includes a long-term observations and interaction with both cows and farmers to understand their communication practices. So the researchers conducted a field work at 10 different dairy farms in Netherlands over several years. So data collection included video recordings, photographs, and detailed field notes, which documenting the interactions between the cows and humans, as well as the interaction between the cows. Then few of the research gaps which I identified in the previous mentioned paper. So for the first one, for the animal whisperer, their accuracy of the model lies on the quality, angle, and clarity of the image, and the apps only analyzes the images, and it cannot process onto the moving images or to the audio. Then for the second paper, for multimodal information fusions for acoustics. So for the study use of relatively small data sets of vocalization, that is from 20 cows, and it may limit the generalizability of the findings. And the focus is on classifying the vocalization into the two broad emotional categories like high frequency and low frequency, which oversimplifies the complexity of bovine emotions. Um, for the third one, for understanding the vocal behavior in the cattle, the author suggested that the study of the vocal communication in the cattle is relatively limited as compared to that of an research on the wild animals. And for the multimodal dairy cow human interaction, this study focuses on a specific population of dairy cows in Netherlands. So the findings may not be generalizable to other breeds or cows which are raised in the different management systems. And the study also relies on the observable behaviors and inference based on the existing knowledge of animal cognition and communication. So, why to understand the cow vocalizations? So, cows communicate through vocalizations such as moves, grunts, and bellows. So, cow vocalizations generally falls within the range of 20 hertz to 2 kilohertz with variation based on the purpose of vocalization like stress, mating, or communication with calls. Then the second one is cows can detect the robust vocal cords which are capable of producing sounds over a long distance. Then cows also has a sense of hearing and can detect a subtle difference in sound frequencies, enable them to identify the individuals within the herds like a human being. So, and the vocalizations, which serves as the multiple functions, which includes like alerting the herd to a danger, attracting mates, and maintaining social bond between the mothers and calves. Cows are also highly social animals with a complex emotional and cognitive capabilities. So they groom each other as a sign of a social bonding and spend times in groups to reduce the stress. Cows exhibit emotions such as happiness, fears, and distress. Also, the cows are considered as more behaviorally mature than pigs and birds because of their longer evolution and development as a ruminant mammals. Their larger brain size and complex social structures reflect higher emotional intelligence and problem solving capabilities. While pigs are also intelligent, their social structures are less hierarchical than cows. Birds, like chickens, have simpler vocalizations and social behaviors as compared to the emotional complexity of the cows. Now let's see some of the acoustics and the linguistic features of the cow vocalization. So, for the acoustic, like cow produces sounds with specific acoustic properties which can be analyzed for a meaning. For example, lower frequency are often associated with calm or neutral states, while higher frequency indicate distress or urgency. Louder vocalizations often signals excitement, stress, or pain, such as during calving or separation from the calves, while short vocalizations often represent immediate needs or warnings. Softer moves can indicate contentment or a desire to maintain the social bonds, and longer calls may indicate, like as I said, distress or the need for the extended communication, such as during a mother-calf bonding. In noisy environments, cow can adjust their vocalization, such as increasing loudness, similar to that of human being raising their voices to be heard in the environment. For the linguistic features, while a cow doesn't use a human-like language, but their cow vocalizations exhibits the linguistic parallels. Like cows may produce a sequence of sounds that vary in a duration, pitch, and repetition, which is potentially forming a syntax to convey the complex messages. The same type of a sound, for example, a move, can have a different meanings based on the context, such as the presence of the calves, feeds, or the predators. Now, let's get to some technical. Let me first tell you what is a large language model. So it is a type of an AI model which is designed to understand, generate, and manipulate the human language. So it belongs to a broader family of transformer-based models, and it has been fine-tuned on enormous corpus of data, enabling it to handle the diverse tasks like translation, summarization, question answering, and text generation. It uses the self-attention mechanism to process sequential data efficiently, capturing both local and long-range dependencies. So LLMs are pre-trained on a massive data sets using the unsupervised learning objectives such as masked language modeling LML, MLM, or casual language modeling CLM. So how does it differs from the deep learning models? So both of them have a unique categories, characteristics, and the capabilities that distinguish them. Like LLM specializes in the language tasks such as natural language understanding and natural language generation. Their general purpose often used as a foundation models for multiple downstream tasks. While traditional deep learning models are broader in scope, focusing on the specific problems like image recognitions like CNNs, time predictions like RNNs, or the reinforcement learning. LLMs, as I said earlier, are pre-trained on large corpora and it is fine-tuned for specific tasks, which we called as a transfer learning paradigm. They benefit from few shot and zero shot learning capabilities. While deep learning models are often trained on the scratch for the specific task requiring a large level datasets. LLM requires vast amounts of diverse and unstructured data for pre-training, and they generalize well on the unseen task or domains through prompt engineering or minor fine-tuning. While the deep learning models depends on domain-specific label dataset, and generalization is weaker as compared to LLMs, so often needing retraining them for a new task. LLMs are designed explicitly for understanding and generating the text with semantic richness, exhibit capabilities like reasoning, summarization, and conversation that can go beyond basic patterns. So why we are using LLM instead of transformer alone for cow vocalizations? So let me answer the question like whether only a transformer based model can decode the cow vocalization. Then the answer is yes. Transformer based models can effectively process the cow vocalization, especially in the scenarios which involves like processing the spectrograms or embeddings of a vocalizations. It can decode patterns in the cow sounds like as discussed by one of the teammates, Venkat, that models such as Wave2Vec or UBirds are well suited to classify emotions or detect specific events in cow vocalization. Transformers can also combine audio and video environmental data to predict cow behavior and emotional stress. Then, why to use LLM for cow vocalizations? While transformers are effective for processing the raw audio data, LLMs add a significant value when vocalizations are interpreted as a part of a broader linguistic or contextual framework. LLMs excels in interpreting structured as well as unstructured text. If cow vocalizations are converted into phonetic sequences or the linguistic tokens or semantic descriptors, an LLM can analyze their meanings and context more effectively. So cow communication is not just vocal, it involves the behavioral cues, environmental factors, and psychological signals. So LLMs are unique capable of translating them between the domains such as cow vocalization to human natural language and from human natural language to cow vocalizations. That is by synthesizing the cow sounds based on the intent. LLMs can incorporate the prior knowledge like annotated data sets, scientific literature on cow behavior, or an IoT based farm data to enhance the interpretative accuracy of the vocalization. Now, let me tell you what is a multimodal LLM. A multimodal LLM is a large language model which is capable of processing and integrating multiple types of data modalities like text, audio, images or videos, and sensor data. So this model uses the transformers to handle the diverse data formats and fuse information across modalities, enabling richer understanding and decision making. So this multimodal LLM can analyze the acoustic features of cow vocalizations. So, like they can understand the features like pitch, frequency, and durations. So, by learning the patterns in audio data, these models can classify vocalizations like distress, hunger, or contentment. Then, the second, we can incorporate video or image data to detect the behavioral cues that complement vocalizations. For instance, A vocalization paired with a pacing or tail flicking could indicate the restlessness or discomfort. Then multimodal LLMs can also map acoustic signals to natural language. For example, this sounds indicates the trust. Conversely, we can also translate the text-based instructions into a cow-like vocalization. And we can also integrate or use IoT sensors like temperature or accelerometer to add the conceptual awareness. For example, pairing a specific vocalization with a drop in temperatures, which might indicate the need for the shelter. So, this multimodal LLMs can learn from diverse data set like vocalizations, video, and IoT data, enabling them to adapt to specific breeds, regions, or conditions. Like a Holstein breed of a cow might have a different vocalization pattern as compared to that of a Jersey cow. So the current approaches to decoding animal vocalizations rely heavily on the traditional machine learnings or unimodal deep learning models, which are limited in their capacity to integrate and analyze diverse data modalities like audio, video, and sensor inputs. This method lacks the contextual understanding necessary to accurately decode the animal behaviors at the vocalization or to facilitate the bidirectional communication. So, in order to address this gap, we propose the development of a universal cow translator by using LLM and multimodal learning frameworks. So, the objectives is the first one is decoding the cow vocalization into human language. So, we will develop a framework that will translate the cow vocalizations into human understandable text or instructions using LLMs. Uh, then we will use the multimodal fusion techniques to combine and analyze these different inputs and tune the LLM to map the acoustics, behavior, and contextual cues to human interpretable outputs. And the output can be in the form of a chatbot or it can be an API to assist the farmers in understanding what does the cow needs and what are the emotional states in real time. The second objective is from human to cow communication, that is, reverse the translation process by converting human language into cow like vocalizations or behavioral signals to facilitate communication from humans to cows. So, like we can use the LLM framework to generate the realistic cow vocalization based on the text inputs, considering the linguistic and the acoustic features. So, what are the to implement? What are the key topics to study? The first one is then animal behaviors and emotions. That how does the cow communicate? What are the emotions like distress, hunger, satisfactions? What are the different behavioral patterns like pacing, vocalizations, the ear and the tail movements? And what are the difference in the behaviors across the breeds like Holstein versus Jersey cow? Then the different acoustic features, that is the sound frequency, pitch, duration and amplitude in cow vocalization, and also the linguistic mapping, and how the evolution of vocalization is happening in cattle as compared to other animals like pigs and birds, and how the cows exhibits the social hierarchies, memories, and what are the learning abilities. Then as a technical perspective, then we need to understand and implement the multimodal fusion layers and the techniques of combining audio, video, text, and IoT sensors data. Pre-train the model adaptation for domain-specific tasks, like how the LLM can generate the human natural text or in converse the audio responses. That is exploring both bidirectional use cases from cow to human and human to cow communications, and what are the different evaluation metrics which will be helpful for the different multimodal models. For data sets, like we need to have a recordings of different sounds, annotate them with the emotional and contextual labels, then have the video footage of cows movement during the vocalizations, and annotate these behaviors with corresponding actions and emotions, and also some of the sensors reading from the IoT data. For the implementation of the projects, we need some high computational resources in order to tune or pre-train the LLMs. For GPU, like we can need NVIDIA A100 or an equivalent. For RAM, we need at least 64 GB, and we can need up to 10 terabytes of data storage to store the data and the model checkpoints. So here is an example of an LLM which is decoding the cow vocalization. So from the Kaggle, I have downloaded the datasets which contains a bovine call. It has an inputs like spectral flatness, spectral centroid, zero crossing, root mean square, and fundamental frequencies, MFCCs. And I have given this data to the most famous LLMs like ChatGPT over here, Gemini and Cloud. So the responses I have attached onto the screen, and the prompt I used here is, can you interpret the cow call and its behavior by using the speech features? And I have given the values for the speech features, which I have discussed earlier. So from the attached image, you can see that LLM has used its previous and pre-trained knowledge and learning on the speech, expressing all the different audio features like what is spectral flatness, how it is used, what are the different MFCC coefficients, and their meaning based on the values. And it has given used that pre-trained knowledge for the interpretation of the call. So almost most of them has specified that you have to use a label dataset because it is a general LLM which is not trained for cow vocalizations. So this indicates that we need a tuning of this pre-trained LLMs for the knowledge of the cow vocalization and cow behavior. So as discussed earlier, transformer-based models can process the raw acoustic of cow vocalizations, but LLMs excels when the vocalizations are contextualized as linguistic or symbolic data. The additional semantic understanding and generalization across tasks and the multimodal integration which is offered by LLM makes them an ideal for developing an advanced systems like universal translator for a cow communication. So by bridging the gap between the acoustic signals and the meaningful language, LLM can bring a innovative age for an animal communication research. Thank you.
All right. Thank you, Mayuri. Questions for Mayuri? It's lunchtime, hungry, no questions. Remarks, if there are no questions, comments, remarks, suggestions for Mayuri and her project. She just started this past September. So she's been here only the 3 months here in Canada. So setting the path for her thesis project. Any sharings you would like to give to Mayuri, tips, suggestions, ideas?
I like the idea, like the thing you're working on. It's interesting.
Okay. Hariesh, it's a kind of similar, little bit of overlap with what you are doing. Yeah. Do you have any remarks? Yeah.
Yeah, I actually I was a little bit. It looked like a very like similar path. So I just can you just let me know, just strike in the mind. So what's the input for the LLM? Like how is it going? Like
So initially, like as I mentioned, it is not just the audio. This LLM will be specifically on cow vocalization, but the input data will be in the form of like audios, the base one, then the behavioral patterns which you are working on, how the behaviors can affect the vocalizations, and also some of the environmental factors like temperatures and the accelerometers.
So it coincides a lot of.
Yes.
Yeah, but getting a realistic data would be a bit tricky. We have some vocalization data, kind of bits and pieces. So coming up with a comprehensive data set that truly represents the realistic livestock farming, which means we have to do data collection. We are starting in February. We are installing, I think, 7 or 8 cameras in Truro. So we will have 30 terabytes of video and audio data every month. So every month we have 30 terabytes. That's a lots of data to analyze and look at it. But again, it's a time start. It's not really a representation of the commercial farms we have visited. We visited 5 or 6 farms in October. You have seen how advanced some of the technologies they use. Cows move around freely, and the amount of knowledge, expertise, and wisdom some of the farmers have. So it's quite advanced. So getting that data would be a bit challenging, but we'll see what we can do. Any other comments for Mayuri? Okay. All right, let's move on to the next presenter, Shreya.
Can you all see my screen?
Yep, go ahead. Yeah.
Good afternoon, everyone. My name is Shreya, and I'm in my first years of Masters of Computer Science. I just came to Canada in September this year. Today, I'll be talking about the digital twins for automated cow nutritionist. This combines the emerging technologies in digital twins and machine learning to optimize the health and the productivity of dairy cows through personalized nutrition plans. Like Harini already mentioned in her presentation, I'd just like to go over it a little bit. Maybe I can skim through it a little faster since Harini did cover most of it. But digital twin is a virtual replica of a physical entity, in this case, a dairy cow. It uses the real-time data from sensors to simulate and predict the cow's health and performance. It uses the real-world data and combines it with engineering simulation as well as machine learning algorithms, which can enhance the operations and can help support humans' decision making. So it basically mirrors the unique physical object or sometimes a process or organization and can help answer what if questions. It can present insights in like an intuitive way and provide ways to interact with the physical twin through the virtual twin. The history of digital twins, it started really like a long time ago, but the word was coined in 2002. So during the 1960s and 1970s, NASA had pioneered the concept of the physical pairing the physical system with virtual counterparts. So this was done during the space exploration programs to simulate and monitor the performance of spacecrafts in real time. The aim was to better understand how the physical systems would behave in the conditions of space. So this concept basically laid the groundwork for what we now refer to as digital twins. In 2002, the digital twin term was coined by Michael Greaves in a presentation in product lifecycle management at the University of Michigan. So in his when he was giving his presentation on lifecycle management, he outlined the potential use of the digital models to represent the physical assets in real time, providing a better understanding of its performance throughout the life cycle of the product. Then in 2010, digital twins began to see widespread adoption. They were largely driven by the integration of IoT technologies, cloud computing, and other real-time data. They started getting into industries of aerospace, manufacturing, and healthcare began to use digital twins to optimize their performance. In 2017, it became one of the top strategic technology trends as industries like automotive industries, construction, and smart cities started to build it. By 2020, the growth had accelerated with applications in agriculture, a few applications in agriculture, as well as personalized medicine and urban planning. And the future is looking into the future, it seems like digital twins will continue to evolve, and the next steps would be to integrate it maybe with edge computing, faster data processing, maybe blockchain to ensure security, and expand the concept of digital twins and the scope to different ecosystems. Digital twins are similar to simulations, but they also differ in many ways. For example, digital twins are dynamic. They are real-time replications. They are continuously updated with data from the real world. It allows for real-time monitoring, analysis, and predictions based on current conditions. So for example, in our case, in the case of a cow, a digital twin can track its health behavior and feeding habits, updating in real time and generating personalized nutrition plans to improve their productivity. They also rely on machine learning and AI to adapt and evolve to make the decisions to be data-driven. On the other hand, simulation models, they mimic the behavior of the system or process under different conditions, but they are not updated on a real-time basis. So simulations are based on predefined scenarios and assumptions, and they are valuable when you're predicting outcomes under specific situations. For example, a simulation of a cow nutrition might predict the milk production based on fixed parameters like maybe weight, age, but they don't adjust to the daily changes in the cow's behavior or the health of the cow. Now, I would like to break down the key components of the digital twin system. First, we have sensors and assets. These are responsible for gathering the real-time data from the physical assets like the animals. The data collected could range from various, it could be environmental to like temperature and health to health metrics like heart rate and feeding behavior. These sensors act as the eyes and ears of our system. They provide us valuable real-time data. Then next we have the data platform, which is the core part of the system. It manages the data, performs analytics, and provides user experiences. The data platform integrates the information from various sources and transforms the raw data to give us actionable insights and makes it available for users so that they can interact smoothly with the systems. The digital twin core capabilities is where what most of the magic happens. It uses the data collected by the platform, and then it creates applications that cater to specific use cases, and it relies on it creates a digital thread based on the information, and it's a cohesive flow of data throughout the life cycle of the asset. And here the asset would be the cow. So to ensure the smooth operations, there is a need for the monitoring dashboard. The operational team usually would ensure that everything's functioning correctly. They would use it for troubleshooting, optimization, or general system maintenance. The enterprise system is what is the backbone of the entire infrastructure. They manage the authentication, security, ensure smooth running, etc. And the use cases are where the real value of the digital system is of the digital twin is realized. Use cases could range from predictive maintenance and health tracking, depending on the industry and application. Now, how digital twins can revolutionize the way we manage livestock welfare would be firstly, real-time monitoring. By using the IoT devices, we can continuously collect the data and feeding patterns and temperature, heart rate, locomotion. It allows us to keep a close eye on the health and behavior of the cows, ensuring that the issues can be spotted earlier. We can also do behavioral and health analysis, where we play a crucial role. Machine learning plays a crucial role here, where we can predict by understanding, detecting patterns, and we can predict anomalies or predict when they are experiencing stress or when they are in their reproductive cycle, etc. We can also optimize their welfare and living conditions by simulating different conditions. We can refine their feeding plans, healthcare regimes, and housing conditions. For example, we can recommend adjustments to maybe the ventilation or the temperature, or suggest changes in the air quality to better the living conditions of the cows. Then we could use it for precision farming and reproduction, where digital twins play a key role for managing these. Like you can manage the fertility cycles, pregnancy, breeding programs. You can get insights on how to ensure the cows can remain healthy, experience minimum stress through these processes. Lastly, by integrating it with AI, they can predict subtle health changes or stress indicators, which usually humans might not be able to see. So we can enable, by using all of this, we can enable data-driven decisions that can improve the overall health and productivity of the herd. The part that I want to focus on is the personalized diet planning for the cows. So the goal was to create personalized nutrition plans for each cow based on a range of factors by tailoring the feed of each individual cow's need, so we can improve their health and outcome and we can also in turn increase their milk yield and reduce the feed costs by optimizing them. The key factors that would influence these plans would be their milk production rates, to understand how the current and historical milk output is, and how the feeding has affected it, depending on their optimal energy needs and nutrient needs that they need. We will also need to monitor the cow's body conditions to understand what their weight is, what nutritional needs are needed to maintain a healthy weight, to improve reproduction rates and avoid metabolic disorders. We would also track indicators like blood glucose, ketones, and other markers, providing insights into the cow's metabolic status. And the type of quality of feed would also be important to understand what kind of food they're being given, and along with the environmental factors like their feed consumption pattern. All of this would be needed to help design the diet that suits the cow's current conditions. Due to the many variables involved, it's almost impossible for farm owners or managers to pinpoint the cause and effect of various feed combinations. However, digital twins can help us simulate the changes in the feed composition and run what-if scenarios to understand the optimal feed intake strategies for a farm. So the significance of this would help all people. Firstly, the cows, it would help improve their health by tailoring their diets. We can address issues like malnutrition, metabolic disorders, and stress. The personalized approach would lead to better milk yield and overall productivity while minimizing the risk of diseases. For the farmers, this would help them make data-driven decisions that could optimize their feed costs, enhance productivity. With real-time feedback, they can also monitor and adjust the cow's nutrition based on live data. This will help the farmers with cost savings and more efficient resource usage. In the broader perspective, for the general public, it benefits from sustainable agriculture practices by improving the cow's health and reducing the feed wastage. Moreover, we could increase the milk production and to meet the milk growing demand and ensuring food security for all communities. In summary, I think the impact of this technology will be transformative. It leads to healthier cows, more efficient farms, as well as more sustainable food system overall. And this also will represent like a huge leap towards the precision farming and smart agriculture, which will help drive advancements for both animal welfare as well as the farm economics. The proposed approach that I think would work is firstly data collection. The first step is to collect relevant data using different IoT sensors. The data that I think I would need would be these. We would need health and physiological data like body temperature, milk production data, which would include historical data of milk yield, quality, frequency. Third would be the feed composition data, which would provide information on the nutritional value, the digestibility, the cost of different feed ingredients, allowing us to design balanced diets while also keeping the cost minimized. Fourth would be environmental data such as air quality, humidity, etc. And lastly would be veterinary and reproductive data, which was including the disease history, breeding cycles to ensure nutrition and health productions. Currently, I am still in the process of identifying open data sets that comprehensively would meet my requirements. Platforms like Kaggle and USDA are potential sources that I am looking into. After the data collection, the next step would be to integrate the data using the data platform. It would be responsible for normalization and storing the data and pre-processing, like imputing missing values or ensuring that the data that is collected is accurate and complete. Next step would be the digital twin creation, where this would involve building the virtual representation based on the correct collected data. It would simulate real-time behaviors and physiological changes using sensor data, allowing for us to track how each cow is responding to the environment and diet. Next would be the nutritional plan optimization, where I would optimize the cow's data to use maybe using techniques like linear programming or different machine learning techniques that can be used to predict the milk yield, detect any anomalies in health behavior, and make any adjustments to the diet plan according to those. The crucial component of the system would be a feedback loop by continuously monitoring the cow's responses to the dietary changes and update the digital twins dynamically. Lastly would be to make a user interface so that I can make this data actionable and provide users with users, that would be the farmers, with an interactive dashboard that displays the actionable insights such as feed adjustments and health alerts, which help farmers make timely decisions. I did read a few papers, and this is how there aren't a lot of papers existing for digital twins that are being applied to agriculture, but there were some that they were particular to livestock care and management. The first one was the AI-based digital twin for cattle care. Here they combined IoT sensors and artificial intelligence to monitor the cattle health and behavior in real time. They used the random forest classifier, which was chosen because of its robustness in handling the complex types of data and sensor noise, and it was making the paper said that it made it ideal for using it for livestock monitoring. The results showed that they did improve animal welfare through early disease detection and optimized environmental adjustments. The next paper was digital twin perception and modeling for feeding behavior. Here they used video data and they ran convolutional neural networks to detect feeding patterns from video data. CNN was selected because of their high accuracy in image and video recognition tasks, and they achieved an accuracy of 95% to enabling them to precise nutrition management for dairy cows. And lastly, was this paper. The paper was by Professor Suresh, where he explored the application of digital twin technology in livestock management. It did mention that the approach of real-time data from IoT sensors, including accelerometers, cameras, temperature sensors, etc., and also how advanced machine learning models and algorithms can be used to analyze these data streams, enabling us to make predictions on health events, breeding cycles, and other critical factors. The outcome of this approach demonstrates that the digital twins can significantly enhance farm productivity and animal welfare by providing data-driven insights. Farmers can optimize their feeding schedules, detect early signs of diseases. However, it did also highlight the challenges such as the high initial cost of implementation and the data integration complexities. These are, while digital twin based automated cow nutrition system offers like a great potential, there are some key limitations that I can foresee and also saw in other literature reviews that I did read, where they did mention that maybe sensors can malfunction and miscalibrations could affect the data accuracy. The cost of implementation is really high to set up the IoT devices as well as the ongoing maintenance of these devices. Data integration will be complex, like sensor data from cows and integrating it with data of the environment of the farm or barn would be a challenge. Also, biological variability among cows may reduce the accuracy. There might be resistance from farmers because they are unfamiliar with this kind of technology, and this might hinder the adoption of this project, as well as the regulatory and ethical concerns that come up with this, like data privacy issues, because there is a lot of data, there is a lot of security issues that come up with it, as well as ethical treatment of animals to ensure that none of these data that we're collecting can be invasive or things that would affect the cows. These were my references, and thank you for listening. And I'm very new to this, and I'm looking forward to hearing your suggestions or any inputs from anyone.
Thank you, Shreya. Questions, comments for Shreya? I know Shreya just started 3 months ago, so she's still figuring out how exactly to move forward. Digital twins for livestock farming is a big, huge area. Harini is looking at a different aspect, comprehensive, because hers is a 4-year project and a very deep dive she has to do. She's been working with a scientist from Switzerland. The YAMPA is an institute in Switzerland developing twin. Shreya's is a master's thesis, so it will be scaled down and narrowed down specifically on the nutrition aspect. So when you look at nutrition, if you read the news, recently there is a company, it's a European-based company. They have been selling a product called Bovaer, Bovaer. Bovaer, if you Google, you will find it. They have been under a heat They say that if you mix Bovaer in the feed of the cow, it can cut down the methane emissions to certain percentage. But the drawbacks, the side effects are not fully studied because of the synthetic compounds present in it. People are also suggesting to include seaweed. So from the ocean, they collect the seaweed. It's called kelp. They mix with fodder, and then they say it can cut up to 30%, 40% of methane emissions. But seaweed also has certain chlorine and other compounds present in it. So longitudinal study, we do not know in terms of the health, but short-term study in California, Michigan, here in Canada, as well as in Europe, clearly says kelp is a very good feed to cut down the methane emissions. So in terms of the personalized diet or the personalized nutrition regimen recommendation tool, digital twin tool you are looking at recommending, you need to consider the climate change, methane emissions, in addition to the milk production and health aspects as well. Also, maybe you could initially start up with what are the common diseases, for example, lameness, mastitis, different kinds of diseases the cows go through. What are the fodder feed we have seen? You yourself have seen. Typically, they go to the field, they cut and harvest the corn, silage, and then they create their own feed. Sometimes they buy specific supplement from a feeding company and mix with the part of the feed. You also see sometimes they mix sodium bicarbonate and other as a solution for the cows to drink for specific management of digestive processes. So a bit more understanding, bit more knowledge, bit more literature review regarding the comprehensive nature of how the correlation between feed and the on-farm daily management. If you can do maybe the past 3 or 4 year paper, like 15, 20 papers, then that would help you to build the digital twin. Okay, how do I proceed further? What are the different challenges one has to look at in developing that twin? A bit more specifics would be achievable.
Yes, Professor.
Any other comments, questions, remarks, suggestions for Shreya? Because if you look at the methane emissions, feed is the biggest, most contributor because of the digestive processes, and also the most expensive. In the poultry also, when the farmers grow poultry chickens, the biggest expense the farmers encounter is the feed. The others are capital, housing structures, the lighting, water, these are routine. Those are not expensive because they get subsidized. Most of them are in rural areas. Feed is the biggest cost farmers have to bear.
Yes, every paper that I was seeing was about optimizing the feed, ensuring that they're getting maximum nutrients in minimum cost.
Yeah. Even for chickens, when you look at it, they say, okay, if you go to A&W, which is an Allen and Wright, which is a famous food chain here in Canada and United States, they have their selling point is plant-based feed for chickens, cows, and pigs. If you go to Burger King or McDonald's, they don't. That's a competitive advantage. Sometimes farmers they feed the animal with the animal product. Sometimes it's also mixed. So they call A&W, Allen and Wright. They say it's a vegetarian diet for the animals. So that's the biggest competitive advantage. So feed does play a significant role. So developing a personalized feeding regimen, digital twin is a nice approach. Harimi, do you have any comments, remarks for Shreya because she is following your food path?
Yes, so I'm just curious about the type of algorithm that you'll be using for your project.
I'm honestly not sure yet. I haven't done enough literature review to know what the best option is. And also, I'm not sure what kind of data I can find available, because I think the algorithm would be very dependent on the kind of data that I can find for the feed, like to predict what feed they should be having or to suggest any personalized diet related to cows. I have to see what kind of data I have available and then find what algorithm fits that data well. But I did see a lot of people, they did use random forest, because I think it was there were data points that were at different scales. So they said that it normalized well as worked well with categorical and numerical different types of data. But I can't say for sure which one I will want to use.
Yeah, because when I was going through papers, filtering down to a certain algorithm was a little crucial. So yeah, I would like you to go through all the papers and just filter out the algorithms. That will make things a little bit easier, because this is like a vast thing.
Yeah.
And I'm exploring digital twin for the first time too. But yeah, that is a suggestion from my side. And
I
as
will
for
keep
the
that in mind.
challenges, or maybe what I went through, the other papers were they were talking about the scalability point of view. So that could also help you in your paper. So, or if you might bring it up in the next presentation, we can have a discussion on that as well.
Yes.
Yeah, how about I suggest Harini, Shreya, you have a separate meeting and call for a meeting with Daniel Onwoode. So involve him because he can contribute in Shreya's project in addition to yours. So.
Sure, sir. Yeah.
Yeah, you guys connect and then chat back and have discussions at a convenient time.
Yeah, sure,
Yes,
sir.
Professor.
Okay, all right, great. So Sibi, your computer is fixed. Do you want to go next? You need
Yes,
to
sir, I can.
go ahead.
Share my slides. I'll just share my screen for this. Sir, is my screen visible?
Yeah, you can see them. Yep.
Yes. Hi, everyone. I am Sibi Parivendan. I am right now working under the supervision of Dr. Suresh. And the topic I'm working on is social network analysis and dairy cows. To give a brief introduction, cows are very social animals, and they interact with each other in very interesting ways, like licking. And these interactions are a way to support each other, alleviate stress. And these interactions are very essential to maintain a general healthy atmosphere in the dairy cow farm, which would be quite important in a healthier population and good production. And right now, I've been working on this project for almost 40 days. I haven't completed my literature review completely. So I will share with you guys ideas I have. And I have organized this presentation as I have shown here. I'll just let you know the methods for data collection that are available right now, and the methods that are used for analysis, and the gaps in knowledge that are available right now, and the possible directions in which I have planned to take the project. So these are the references I have completed till now. And the knowledge I am going to present in this presentation is mostly going to be from this. This is the layout of a freestyle barn, where cows are put together in separate feeding and non-feeding zones. And you can see like the milking parlor, collecting yard, and everything in here. The methods used for data collection are primitive methods, where the manual methods which were used earlier, where a group of observers go to the dairy farm and they use some methods like scan sampling, and they note each pair of cows, and they note of the cows which are close to them as their companion, and they maintain a tick sheet of this cow has interacted with this one and everything. This process goes on for days or even weeks. And after a period of weeks, this data is uploaded onto computer into digital form for later analysis. That's one of the primitive methods. And continuous observation through cameras, where the cows are monitored through cameras for an elongated period of time. And then they use analysis softwares where people can automate some sort of sorting or looking through the videos. Though it is a lot of manual work, through the analysis software, the process can be automated a little. And then for a few research projects, they got data directly from the research facilities. The research facilities maintain a lot of data related to the cows, like pedigree, their nail trimming records, their pregnancy status, and everything. And the most prominent techniques that are used these days is PLF techniques. PLF stands for Precision Livestock Farming. Initially, GPS was used, but as everyone knows, GPS has an accuracy of maybe at most 5 to 10 meters. When the accuracy is worse than 2.5 or 3 meters, proper proximity between the cows can be detected. If you see here, this proximity would be maximum of 2.5 meters or 3 meters based on the study. So 5 meters doesn't make any sense over here. So GPS is not used these days. And second form of data used in some papers is the movement through sort gates or simply gates. If you see here, this is the non-feeding zone, the feeding zone, the collecting yard, the milking parlor. Cows have to frequently move between these areas, and there are gates between each of these areas, which would note the RFID of cows and maintain a record of which cows are passing through them. And this data can be used to find which cows are present in which areas. And while passing through them, there are video cameras present in those gates. Through those cameras, they will find which cows were in close proximity to each other to build a connectivity relationship between cows. And the electronic feeders and water bins in the feeding zones, while the cows come to take feed, they have some sort of monitoring over here. And the most prominent methods used nowadays is through the ultra-wide band proximity sensors, where the cows are fitted with weighted neck collars, and they have these ultra-wide sensors attached to them, which would be continuously emitting some radio signals. And there would be separate sensors to pick up those signals. And using the triangulation method, the approximate location of the cow is identified. Exact location, but it will be subject to a little bit of errors. These are the normal methods used for data collection, and this ultra-wide band has been the most prominent method as far as I've read in the 9 or 10 papers in the past 3 to 4 years. And social network analysis involves building a graph like this. I will get to what this graph is in a little bit. And I already mentioned about the proximity interactions between cows. So these proximity interactions, when these two cows are together for maybe a period of 60 seconds, it is considered as an interaction. And for a whole day, the number of such interactions are counted for each pair of cows. And if those cows had interacted, these points are all individual cows, and these edges are interactions between cows. If these two cows had interacted in that day, edges drawn between them. And thicker the edge, the larger number of connections between them. Larger number of interactions between them. It's an example of the social network. And there are a lot of evaluation metrics for a social network, which is prominently used in social network analysis. Some of them are diameter, density. Diameter is nothing but the shortest distance between two cows. The density is the total number of connections that are actually present in this network divided by the total number of connections that can theoretically be present in the network. And degree centrality is the number of nodes each cow is connected to, or number of cows each cow is connected to. And the node centrality is like, the number of areas the cows act as bridge between for connecting. And Wood's lactation curve is an interesting model which would give an approximate data flow of how the lactation proceeds in a cow. The lactation after calving, the initial milk production in a cow is a little bit lower, and it gradually increases to a peaking point. And after it reaches the peaking point, it gradually decreases until the 30 days before the next calving. This would be represented by the Woods lactation curve. And some linear mixed models are used for analysis. The linear mixed models are basically some linear regression models with some randomizations involved with them to account for some outliers and stuff. And node-based permutations rank some mantle tests. Node-based permutations are like we have to, when we have to find in a data set if the distribution is random or no, we use the node-based permutations. It's like there is you want to rank 100 cows interactions based on their lameness. There are 40 lame cows and 60 non-lame cows. What we do is we initially find the statistic we need, maybe the sociality, which is the number of interactions total between each cows divided by the number of days, which would give the average sociality in a week. Weighted by the lame and non-lame cows. What you do next is you permute the lameness tags between these cows. So initially, the lameness tags which were present on the 40 cows would be distributed randomly to other cows. And when you calculate your statistic of interest in this sense, there must be a fine difference between the initial statistic you calculated and the next statistics that is being calculated after the permutation. The difference would suggest that there is the distribution is not random. And similarly, rank some mantle test and the Pearson correlation are used to find the level of correlation between two groups or two measured statistics. And multi-level and linear logistic regression models are a combination of linear regression and logistic regression models in some fixed order to account for some calculations. And this STRGM model, this separable temporal exponential random graph, is basically a framework for identifying the predicting how the connections are gonna be formed from a present network and how persistent the present connections would be. And network triangle is like in this graph we consider dyads which are the interaction between two cows. The network triangles would consider the interactions between three cows. It gives good accuracy in some places. And stochastic actor-oriented models is one such model where each node is given some random function and they can think for themselves. It's like the actor-based models in reinforcement learning. And some of the knowledge gaps I identified by reading the 10 papers or so, or the proximity is taken as a measurement for interaction between two cows. That is, we assume if two cows are close to each other, they have some form of interaction in general. But there is no way for us to know whether the interaction is affirmative or agonistic, because the cows may be pushing against each other or licking each other. There is no way for us to know that. There are some previous studies which suggest just that both displacement and licking can count toward the total number of interactions between two cows. But still, having a qualitative differentiation between them could give us better insights. And the second knowledge gap I've seen is the network construction from video data has not been a very prevalent area of study. Some work has been done over there. I recently saw publications from 2023 and 2024, but it's not being used prominently. The ultra-wideband sensors, the proximity-based sensors was the most prominent source of data collectors. From video data, if you're able to collect the movement of cows, the network data and everything, the monitoring would be very efficient. The initial cost of installing these IoT sensors would be decreased. Also, the maintenance cost would be decreased. And the third knowledge gap I've identified is the strength of the social network based on the functional zones. Consider this a dairy farm. These blue colors are the cubicles where the cows rest. They are the resting areas. And this yellow color area is the feeding area or non-resting area you can consider. There is a stark difference between how cows behave inside these feeding areas and outside these feeding areas. This is a good area of study, and I have seen some papers having controversy over the general behavior. I'll explain it later. And based on these, my tentative directions in which to proceed my study are one is the real-time object identification detection from the video data in a dairy cow farm. There has been a paper, I read it, which has fitted 8 cameras on in the dairy farm in this manner on the left side and right side. So there are no blind spots left. And with this video footage, there are a lot of manipulations done to obtain the information. I'll explain them. The steps involved are the image pre-processing. The first one is the camera calibration. We may consider this point the origin, and the camera is present over here. So we have to fix this camera's point based on the real world point. And that is basically called calibration. Not just this, adjusting focal point and everything. Those are to be done in the software. And next is image rectification. The camera, based on the conditions they were placed in, there may be distortion, like the angle may be wider or vertically more, traversally more. Those parameters are controlled using the distort function. To do these things, we must have a proper knowledge of the camera being used and the conditions they were used in. And the third step in the image pre-processing is sample selection and annotation. Among these video footages, there are particular images selected over different time periods, and no matter how much number of cows there are, 100 or 200, people manually set the coordinates of each objects present inside the image. And it's a manual process, but the data set, that's how the data set is created over there. And then perspective transformation, top-down view. This is one of the most important steps because this video is taken from the left and right side of the barn. There is the transformation done to make sure the cows are always imaged from the top view. It is possible right now. Always the upper back part of the cow would be visible in the video. And object detection is done using the top view of the cows. And it's done using convolutional neural network and efficient data. I am not sure about the working of this, but that's what mentioned in the paper. And then the objects are continuously tracked. They detect objects in one time frame. And in the next time frame, when they detect the objects, they detect in close successions to each other. And they find the Euclidean distance between each pair of objects, and they determine the closest Euclidean distant object to be the object from the previous video. And in this manner, the video is continuously monitored. But there are some errors that could happen over here, which is like there may be multiple images with the same Euclidean distance, or there may be no images with a close Euclidean distance. There may be some video footage lost in between. And that's a limitation. In that case, what they do is they have the cow tracked till this time frame, and then the cow is lost, and there was a random ID assigned to the new cow that was being found. And when the next time when they enter the milking parlor, their ID would be recorded, and these two behavior observations would be merged together. But there is a limitation in this aspect. before they enter the milking parlor, what if there were 1, 2, or 3, or 4, or even more segments? In that case, the data would be lost. There would be some sort of algorithms to find the lost data's proper connection based on the time frame and maybe close connection, some intelligent algorithms. But still, a more reliable approach would be if you are able to identify each cow separately. This is what I have planned on trying to implement. There has been some study based on it. It's basically like the cows on their backs have a lot of unique patterns on them, the black and white patterns, HF cows. And these patterns can be effectively read by convolutional neural networks, and they can be used to uniquely identify each cow. So what we'll have to do is we'll need if you are taking 100 animals in a dairy farm, we'll need the angle of 6 angle images of each cow, or else a video of the cow in 360, and we'll have to take up frames of each side of the cow. And we'll have to make the neural network learn the cow, and when viewing through the camera on top-down view, we'll be able to identify each cow separately. And when each cow is identified separately, we can merge with the previous detections, and continuous video can be monitored with them. After that, these assignments are tracked, which is assigning new IDs and making new hidden IDs and merging them with the old ones. If we do this perfectly, then we'll get a continuous video of the cow movement throughout the entire day. This is one of the directions I have decided for the project. And the second direction is differentiating between affiliative and agonistic interactions between the cows. I haven't done a lot of reading in this, but it's a direction I have decided to work on. And third direction is the functional zone-based study. In 2 papers I had mentioned above, in an initial paper, sorry, I forgot the names. Sorry about this. Rocha 2020 and Marina 2024. In the Rocha 2020 paper, they studied how constantly maintained pen would have social network connections, and how the pens which were continuously undergoing changes would have the social network connections. And the interactions between feeding area and the resting area was one of the areas of the study over there. And from their findings, the connections or interactions in the feeding area were quite sparse, and the ones in the resting area was quite stronger. But there was some justifications, like a hypothesis they had provided, like in the resting areas, it's a cubicle of 28 cubicles for 26 cows. So naturally, the cows have to stay close to each other. Since it was a proximity-based connections, the cows would basically be staying close to each other, and they could have gotten a false result since the cows are always close to each other. Whereas in the feeding area, the cows decide their own timings when they want to go out. The movement is high, and the time they spend in the feeding area is really low. So that may have been the reason in this case why the network is sparse in the feeding area as compared to the resting area. And in the study with Marina 2024, it was a different study. It was in a freestyle ban with a really large area. They had to find the effect of parity and some other pregnancy in the social interactions between each cows. But from one of the results, it was evident that in the feeding area, the connections were more closer than in the resting area. However, the betweenness ratio in the resting area was higher. The betweenness is how much a cow is connecting two different groups together. That's the betweenness measure. in the feeding area, the closeness of the cows, that is the number of interactions between particular pairs of cow, was higher. This may be attributed that in the feeding area, the cows are free to choose who their companion is, and the resources are limited in feeding area, like the trough where they can take feed or where they can consume water. The resources are really limited, and so the cows may have to stay close to each other. And in the resting area, this was a freestyle one, and it was a large resting area. So the cows didn't have to stay close to each other. They can choose where they can lie, and so that may have been one of the limiting factors, but it wasn't proven evidently. So this can be a good area of study. That is the functional zone based, how the social network prevails between the feeding area and the resting area. So these three are the areas I have taken for now. And surprisingly, this first direction I've chosen coincides a little bit with Shubhangi's. That's why I had a little bit of questions why she had chosen face to be the factor. And so I'm still working and studying a lot of papers regarding these three areas. And these are the currently identified data sources, this Kaggle data source. A couple of persons have been using this, including Hariesh mentioned the same data set, CBVD5. And this is a data from the reference 3. It was the human observed data. And there was a website, it's not a reliable source. And to do the study, the direction I mentioned in the first direction, the data required is I'll need the continuous data of a dairy farm, at least one complete day, with the cameras, at least 8 cameras without, at least 6 cameras without leaving any blind spots. And if there were 100 cows included in that study, I'd need all perspective images of all of the 100 cows, plus their AMS data when they entered the AMS and when they exited the AMS. Also, the camera's configuration. With that, I'll be able to build the model. But for now, I can try working out with this Kaggle data set till then. And sorry, I forgot to explain one thing. In the real-time object detection, how they identify the milking parlor is they track the nodes entering the milking parlor and exiting the milking parlor, and they match the timestamps of when they exit the milking system, and they match it with the record of which cow had left the milking at that particular point, and they assign the exact ID to those cows. Yeah, that's mostly my work, and these are the further papers I have decided to plan to study. And thank you. If you find any similarities with my project and you want to discuss something, feel free to contact me anytime. And I have just started out, so I am open to any suggestions. If you have any questions, I'm...
Okay, thank you, Sibi. You mentioned that it's not reliable, and then you said Dairy Brain, Wisconsin.
Yes.
That's a very reputed group. It's a bunch of researchers within University of Wisconsin-Madison, but there is also other researchers from other universities they contribute. It's very much reliable, trustable, reputable group.
I mean, reliable in the sense we may not get the data we require exactly without some financial constraints in that manner. I mentioned it as
have you made an attempt to communicate with them and request? Usually they are open-minded. They would be more than happy to share. We just need to cite their papers in your work. That's all the expectation is. So it's just reaching out and asking. If we don't ask, we don't know whether we are going to get or not. If we ask, the only two choices they have, they can say no or they can say yes. So if there is no harm in asking, requesting, hey, I find this data from your paper interesting. Would it be possible for you to share a bunch of videos? This is the project I'm working on. I would make sure that I would cite your papers, give proper credits. So there is absolutely no harm in asking. So please feel free to ask. We are also
Sure,
going
sir.
to what we call as a data availability. Whenever we publish our research, we also have obligation because to make the data openly accessible. If you look at Bubakar's paper, he made everything available, the Excel sheet, the number of emissions, algorithms, everything is made publicly available. So that's an expectation nowadays. So data availability, there is also a responsibility for researchers to, at a reasonable way, if there is confidentiality clause, if there are certain issues, we cannot. But most of the time, people would be more than happy to share the data.
Oh, sure, sir. I'll try them too.
Okay, comments for Sibi? Questions? Oh, it's 5.5 hours. Leave me alone.
Guys, I am open to suggestions. If I was vague in any part, if you didn't understand anything, something, please feel free to say. I can make it better next time.
All right. Okay. So it's a really good job, you guys. 5.5 hours you have been sitting and listening to each other. That's fantastic. You have demonstrated resilience, as a human being, as a young student. That's fantastic. Couple of announcements. March 12th, I know Bubakar and Hanching would be away, but we have a research day presentation scheduled at Truro campus. Even if you cannot physically present, just send the poster file, Hanching and Bubakar. We would be able to put up the poster for you so you can add 2 lines in your resume that under the conference presentations that you did present in that event. So it add value to you. So feel free to send the files at least 2 weeks before the 12th of March. Those who are new, try not to present just the research proposal, no Mickey Mouse posters. Some preliminary data has to be shown, some analysis has to be shown. So please make an effort. You have about 3 months left. Even whatever scale, try to present some results because if we slowly build on to your thesis. I know holidays are approaching. If you guys are up for it, maybe we can meet physically this Friday at Halifax in one of the restaurants. Unfortunately, Bubakar is far away, 3.5, 4 hours drive. He can't make it. But others, probably Prajesh is also based in Truro. Shubhangi is even further in Toronto. But I think the rest of us, we can meet for a dinner at 6 o'clock on Friday evening. So I'll send an email. Let me know what would you prefer, whether you would be able to meet or not. Then we'll just have a holiday celebrations. I know this is the last week for most of you are wrapping up exams, reports and assignments. So Friday would be a good time for us to connect, recharge, and celebrate before the holiday period hits. Any other comments, suggestions, anything else you guys wanted to say?
Professor, is it possible to do it next week? We have an exam on Monday. After that, we're free. Our last exam, me and Mayuri both have our exam on Monday.
Okay. It's only, 2-3 hours. Anyway, you have to eat, right? You don't have to cook. You just come eat, have a good time and then you go. Because you haven't met physically with the other lab members, it's an opportunity to connect. Next week, or some of us would be away as well. Yeah.
Makes sense, yes.
Okay. All right. Okay, you can go and grab your lunch or drinks or whatever. Have rest. See you guys. Bye.
Thank you.
Thank you. Bye.
Thank you.
Thank you, Professor. Bye bye. See you.
Thank you.